Hello everyone and welcome to Robotics, Mechatronics and Robot Operating System version 2 or ROS2 tutorials. In this ROS2 Jazzy tutorial, we explain how to write a C++ program and a ROS2 package from scratch that demonstrate how to implement all the components of a system for controlling a robot. In particular, we explain how to implement a C++ class that embed. Number 1. A ROS2 subscriber object for receiving sensor information from the robot and a ROS2 publisher object for sending the control information to the robot. Number 2. A callback function for reading sensor information. The sensor information consists of the current position, orientation, and velocity of the robot whose animation is given over here. This callback function is activated every time there is sensor data on a ROS2 sensor topic. This callback function adds the feedback loop to the system. And over here you can see the received feedback information. You can see, first of all, X and Y positions of this robot on the screen. You can see the theta, which is the rotation of this robot with respect to its z-axis. You can see delayed linear and angular velocity, and you can see a timestamp over here. Note over here that linear and angular velocities are zeros since we are actually measuring at the moment where this robot is stopping. That is, we are measuring with very coarse frequency whose period is 2 seconds. You can significantly speed up this and you can measure every milliseconds, or even you can use a shorter period. Number 3, a timer object for ensuring that the control function is called at fixed time steps. This function is important for enforcing and for precisely controlling the desired control frequency. And number 4, the controller function which implements the control method. In this tutorial, we implement constant control signals. However, everything explained in this tutorial can easily be generalized to the case of implementing feedback control algorithms such as position, velocity, PID, LQR, and other control algorithms. As a proof of principle and as a model of a 2D mobile robot, we use a turtle sim simulation, which you can see over here. The turtle sim simulation simulates a 2D mobile robot. It enables us to quickly test and prototype control algorithms before proceeding with the next step and testing algorithms in a gazebo simulation environment. In this tutorial, we explain how to implement a simple control algorithm that will make the robot describe the circular trajectory that you can see over here. However, as mentioned previously, you can easily change your code and implement almost any algorithm. All the components are actually implemented in a class. You just need to change some parts. The main motivation for learning the material presented in this tutorial comes from the fact that all the implementation steps explained in this tutorial are the implementation steps that you will perform on a real robot. That is, to control a mobile robot, you will need to write a C++ code and functions that will read sensor information and that will send control commands. Later on, you can modify our code files presented in this tutorial and adapt them to a specific robotics application. In this tutorial, we explain how to implement a ROS2 package from scratch and this C++ program and this C++ class over here that implements the control algorithm. In addition to this, we created a manual shown over here. This manual is 12-page long, and this manual contains all the commands that you need to write in order to develop the package and to implement the code. That is, the manual is written for people who literally do not know anything about ROS2, about C++, etc. A link to this manual, to the code, and to all the package files will be provided in the description below this video. Here is the license and the copyright notice. This document, develop code files, lesson video, and all the provided material referred to as learning material in the sequel should not be copied, redistributed, or publicly posted on public or private websites, code repositories, and social media platforms. Also, the learning material should not be reproduced manually or automatically from this video and then posted on public or private online repositories. The provided code files and learning material are the ownership and the original work of Dr. Alexander Haber, who is the author, and they are for personal and non-commercial use. You have the right to use the provided code files and learning material only for personal educational use and strictly for non-commercial use. The code files should not be used for commercial purposes without paying an appropriate fee to the author. The code files and the learning material should not be used as lecture material on online learning platforms and in official or unofficial university courses. Without the permission of the author and without paying an appropriate fee, the provided code files and learning material should not use to reproduce academic papers, student reports, or other documents. The provided code files and learning material should not be used to train an AI algorithm or a large language model. Okay, let's start with implementation. First of all, let's clarify what are the prerequisites. To implement the material presented in this tutorial, you need to have, number one, Linux Ubuntu 24.04. Do not use Windows Subsystem for Linux or WSL since you might have issues displaying graphics. Install Linux Ubuntu on your computer. If you have a Windows computer, then you can easily install a Linux Ubuntu in parallel to the Windows operating system by using a dual boot approach. In fact, on my YouTube channel, you have a number of tutorials explaining how to properly set up Linux Ubuntu and how to set up a dual boot option. Let's verify that you have the correct version of Linux Ubuntu. To do that, click here, then search for terminal, open the terminal, and over here in this terminal, verify your Linux Ubuntu version by typing this. And you should see Ubuntu 24.04. This last number really doesn't matter. Then, number two, you need to have ROS2 Jazzy Jalisco installed on your system. Let's verify that ROS2 Jazzy is properly installed. If not, then again, on my YouTube channel you have several video tutorials explaining how to properly set up ROS2 Jazzy Jalisco. First of all, type this command, and if ROS2 Jazzy is properly installed, this command will list the content of this installation folder and you should see this. However, this is still not the final test. The final test and the appropriate approach is to try to source the setup.bash file, and I'm going to explain the purpose of this file later on. However, for the time being, just type this and then type this. This will print the ROS distro environment variable, and if you see Jazzy, this means that ROS2 Jazzy Jalisco is properly set up and you can continue watching this video tutorial. If not, then install ROS2 Jazzy Jalisco. Okay. The first step is to install and start TurtleSim node and simulation. To do that, click here and search for terminal. But before we actually start the TurtleSim simulation, let's briefly explain what is an underlay. The underlay is a basic ROS2 configuration and a set of parameters created and defined by sourcing a setup script provided by the standard ROS2 installation. The underlay provides the necessary build dependencies, libraries, and packages necessary to execute the ROS2 commands and build packages using the Colcon build system. The underlay is created by executing this command. We executed previously this command. However, since I opened a new terminal, I will execute again. And remember, every time you want to play with ROS2 or to do something, develop a package, write a code, you first need to run this command. And this will source your environment and create the so-called underlay. After you create the package and compile everything, you will need to execute another source command, and you will need to execute another setup.bash file. However, this time this setup.bash file will be setup.bash file from the package that you just created, and this is called an overlay. That is, the overlay is a configuration and a set of parameters that enables us to execute programs and nodes of the created package. Okay, so let's first install the TurtleSim package. Most likely the TurtleSim package already comes with your ROS2 installation. However, it's still a good idea to try to install it. Remember, Whenever you want to install something on your Linux Ubuntu, you need to update and upgrade by running these two commands. Enter your password and wait until this is completed. And press Y here. And this will install and actually update and upgrade everything such that we can nicely install everything. To install the Turtle Sim simulation, you simply need to run this command. And then let's verify that the Turtle Sim simulation is installed by running this command. And you should see all the programs and all the executable inside of this package. You can see draw, square, mimic, turtle teleop key, and turtle sim node. For us, the most important is turtle sim node. This is actually a node that implements the simulation and creates a graphics user simulation or graphics user interface. So let's run this command. This command will do the following. It will perform the following. ROS2 run, this means that we are running something inside of ROS2, then we specify the name of the package, it's turtle sim, and then we specify the name of the executable, it is turtle sim node. And if you press enter, magic will happen. You will see this nice simulation screen and you will see our turtle representing a two-dimensional robot. And this turtle can move inside of this plane. Now, try to use your keyboard keys and try to move this simulation. Well, you will not be able to do that. Why is that? This is because we didn't enable another node that will control this simulation. There are several ways to do that. You can either run this node turtle teleop key and you can manually move this robot by using the keyboard keys. We are not going to follow that approach. Instead, we are going to write a C++ program that will move this robot. We can control the position and orientation of this robot by sending the linear velocity and angular velocity commands to this simulation. These commands are sent through an appropriate topic. We need to find out the topic name. To find out the topic name, let's open a new terminal while keeping this original terminal running this simulation open. That is, don't close this terminal. Just click here to open a new one. And again, since we want to play with ROS2, you need to source your environment. That is to create an underlay. And then to list all the topics that are currently active, let's run this command. And you can see this. You will see these turtle1 topics. We have command velocity, and this is the topic that's used to control the turtle. Then we have another topic, turtle1 pose, and I'm going to explain the purpose of this topic later on. For those of you who don't know what are topics, you can imagine topics as channels, or better to say as communication channels, sending and receiving information, that is in both ways, sending information between nodes. And nodes can be seen as programs that communicate. In our case, turtle1 command velocity is a topic that will send control information to this node, and this is the turtle sim node. And by sending appropriate commands through this topic, we will be able to move this robot. We will use this precise name in the C++ program for controlling the turtle sim node. The next step is to figure out the type of ROS2 messages that are sent through this topic. To do that, you simply need to call the command ROS2 topic info, and you need to specify the name of the topic, and if you press enter, you will get a very valuable information. You will see first of all the data structure that's being sent through this topic. It is geometry message twist. That is, we are sending twists. We will see what are the twists later on. Another important thing and another important information that currently we don't have any publisher publishing messages through this topic. This is because we didn't write our C++ code. However, we have a single subscriber, and that subscriber is precisely this node over here generating this animation. Next, let's learn and let's figure out what is actually the twist. And let's try to figure out what are the components of the twist. Well, to do that, you need to run this command. So type ROS2 interface show, and then you need to specify the data structure name. And if you press enter, you will see a very interesting thing. Let's read what's written over here. This expresses velocity in free space broken into its linear and angular parts. You'll see linear vector and you'll see angular vector. So what is this? Well, if you studied mechanics or if you took physics class, you know that there are several types of velocities. There is a classical velocity, or how they like to call it, linear velocity. This is the first derivative of the vector of position with respect to time. And the second type of the velocity is the rotational velocity or the angular velocity. However, the angular velocity is actually represented by vector in mechanics. And you can see over here this simulation, and you can specify the linear velocity and the angular velocity. Now, since this is a two-dimensional simulation, you will only have an x and y components of the velocity. Namely, the coordinate system is oriented like this. X and y are inside of the plane of your screen, and the z is pointed out toward you or toward the computer. That is, z line is perpendicular to the screen. Consequently, since we can only move this simulation in two-dimensional space, we can only set an x and y component, as z by default is 0. When it comes to angular velocity, this robot can only rotate with respect to its basically center of symmetry. That is, you can imagine the z-axis is located over here at the center of this robot, oriented toward you. And by specifying the angular velocity, you will specify the change of orientation of this turtle. That is, the turtle will rotate around its axis. And another very important thing to keep in mind is that x, y, and z coordinate system is actually a local system, or the base, not the base, it's actually the body coordinate system, to be more precise and to use mechanics terms. And that body coordinate system is attached to the center of the mass or the center of the symmetry of this robot. That is, this is the coordinate system that actually moves with this robot. On the other hand, Turtle Sim is a simulation that contains a virtual sensor that measures the robot position, that is, x and y coordinates, robot orientation, angle of rotation of the robot body, linear velocity, and angular velocity. Next, we need to discover the name of the topic that is used to communicate this sensor information, since we will implement a C++ subscriber that will read this information. This information is necessary in order to develop a feedback control algorithm. Again, we need to repeat the previous command. Let's again repeat ROS2 topic list. And again, let's analyze these topics. For us, the most important topic is Turtle1 pose. Okay, so let's obtain more information about Turtle1 pose by typing this. And you will see what's happening. We can see the type of messages or the data structure that's being transmitted through this topic. It's Turtle Sim message pose. That is, this is a pose. Now, if you studied mechanics, for you pose will be very well-known concept. However, for people who didn't study mechanics, pose might be confusing. So let's obtain more information about the pose, and let's see what it is. To obtain more information about the pose, you need to type this. And then you will see what the pose is. Let's bring back this, basically this simulation, and let's analyze. So what is the pose? Pose gives you xy coordinates of the center of this turtle with respect to some coordinate system attached either in this corner, this corner, this corner, this corner, it really doesn't matter, and gives you the orientation angle. The orientation angle is the angle that this turtle makes with x-axis, and the x-axis is actually the global axis or the x-axis of the base coordinate system, which can be here, here, and here. For example, over here, you can see that theta is 0. Then Pose also consists of the linear velocity and the angular velocity, and this is basically the absolute velocity with respect to this coordinate system over here. This is not the relative velocity with respect to the local coordinate system, since this velocity is always zero. So again, when someone gives you the pose information, it's actually x, y, and theta, and linear velocity and angular velocity. And again, keep in mind that x and y is given with respect to the base or the fixed coordinate system, and that's the pose. That is, the pose consists of 5 components, and we will need this information to develop our. Now that we have obtained enough information about turtle sim simulation and about the relevant topics, let's continue with the step number 2. The next step is to create a ROS2 C++ package and a program for controlling the turtle sim simulation. Here, it's very important to keep the terminal open in which the turtle sim node is activated. That is, keep this original terminal open, otherwise this simulation will be closed. Always keep in mind that thing. Okay, so here are the steps that we need to perform. First of all, we need to source the environment and create the workspace folder. Then we need to create an empty package folder structure and required files. Then we need to implement the source file. Then we need to modify cmakelist.txt and package.xml files. And finally, we need to build the package and source files by using build command. In the sequel, we will explain all these steps in great detail. Okay, so let's start from scratch and let's close this terminal. Let's open a new terminal, and over here let's practice sourcing the environment. Okay, whenever you want to start, create an underlay. Then let's go to the home folder, and in the home folder let's run this command. This command will actually create 2 folders. It will create the base or the workspace folder called ROS2_WS, and inside of that folder it's going to create a source folder. Here it is. Good. So let's explain what are the purposes of these folders. So let's navigate to ROS2WS and let's see what we have inside. We have the source folder. All the source files will be placed inside of this folder, and we will navigate to this folder when we create an empty package. On the other hand, when we want to build the package, we always need to go back to the ROS2WS folder, and you will see that just in a moment. Okay, since we want to create an empty package or a package template, let's first navigate to the source folder, and of course you will see that the source folder is empty. And over here, let's create our empty package. We do that by executing this command. We call ROS2 package create, then we specify the build type. This is the standard build type, and cmake, and over here we need to specify the node name. This is the node name, and you have a complete freedom to select the node name. However, follow this tutorial and implement exactly this node name. And when you press enter, you'll see that magic will happen. And let's see what happened. Expand this and just analyze. Okay, package name, test node, destination directory, version, description, licenses, and here something is being created, some files and folders, and very interesting. Okay, so let's again type here ls/la and let's see what happens. There is something else over here. So we created a new folder. So let's navigate to this folder and let's see what's happening inside. Wow, we have some cmake files, we have include, we have package XML. For the time being, the most important files are cmake lists and package.xml, and in addition we have this source folder. We are going to place all the source C++ files inside of this src or source folder, and later on we will modify cmakelist and package XML. Before I continue, I need to explain the following. First of all, let me go back over here to this source folder. And instead of the command I just executed, you can execute another command. Namely, you can execute this command. However, don't execute it, just watch what I'm saying. So you could execute this command, ROS2 package create, build type m and cmake, then the name of the node, and then over here you can set manually the dependencies. You need to set RCL CPP, turtle sim, and geometry messages. Don't execute this command. I'm just explaining what is an alternative way for creating a package. Now, in this way, that is by executing this command, we are explicitly specifying the dependencies while creating the package. I don't like this approach since I like to manually control my dependencies, and I'm going to later on enter these dependencies in CMake list and package XML. This command will help you a little bit, and it will add automatically some dependencies to these two files. However, as I will show you later, we are going to manually set the dependencies. So just as a side note, these dependencies are actually the standard ROS2 packages that our program and our complete package will depend. And this will be explained further in this tutorial. Okay, now that we know how to create packages, that is how to create the templates, we need to implement the source file. To implement the source file, you need to go to this folder and note over here that the folder name is precisely the name of your package. And then you need to go again to the source folder. And inside of this folder, which is currently empty, you need to create a C++ file. Now, over here you can use your favorite C++ editor. In my case, I'm going to use Visual Studio Code. To start Visual Studio Code, I need to type this. Most likely you don't have Visual Studio Code on your system. However, I created a separate video tutorial explaining how to install Visual Studio Code on Linux Ubuntu, and you can find that tutorial by simply going to my YouTube page and searching VS Code Linux Ubuntu install. You don't need to use Visual Studio Code, you can use a simple editor. And over here we need to create a new file, click on new file and call it as test.cpp and press enter and save this file inside of the source folder and click like this. So again, make sure that the file is saved at the proper location. So if you go back to your, let's say, home folder, here's your workspace folder or the base folder, then you have one source, then you have another folder which is your node, then you have the source folder, and here where the file should be saved. Okay, and let's implement the file. To save time, I simply paste the code we wrote. This code is the original work of Dr. Alexander Haber, and a link to this file is given in the description below. Over here, I'm going to skip these comments and I'm going to start with the first line over here. RCL CPP is the ROS2 client library for C++ that is included with any standard installation or with any standard ROS2 distribution. RCL CPP provides the standard application programming interface or API. Then, we need to include this header file. Let's explain what are geometry message twist. Now, if you go back in this video tutorial several minutes, you will see that once we investigated the topic for sending the command velocities or for sending the control signals, you will see that the data structure that is being sent through this topic is geometry message twist. And this is very important. To use this data structure, that is to define objects, we need to include this header file. Now, just to remind you, twist is a data structure containing components of the linear and angular velocities vectors that are used to control the 2D mobile robot. And this is sent through this topic over here. And make sure that this is the correct name of the topic, since maybe in your implementation or maybe in some little bit newer version of ROS2 Jazzy Jalisco, here might be written Turtle 2 or Turtle 3. Or if you open several Turtle simulations, maybe you'll see Turtle 1 and Turtle 3. So make sure that this name is correct. Okay, next, if you again go back and watch this video tutorial a few minutes ago, you will see that we also investigated the topic that's used to communicate pose information from our turtle sim and through this topic called turtle sim 1 pose. And you can see that the type of the message is actually turtle sim message pose, and consequently we need to include this header file. then we need to include this header file in order to work with time functions. And then over here we need to say this is the placeholder for the callback function input parameter, and I'm going to use this later on in the code. And then for time we need this line over here. And here's our class. I believe that a lot of viewers of this video are not proficient with C++. Consequently, I will spend a little bit more time explaining basic C++ concepts. Over here, we are actually defining a class whose name is controller node, and look here what's happening. We are saying public RCL-CPP node. So this means that this class over here is actually inherited from this parent class node. And this is a standard practice. That is, whenever you want to define your own node, you're going to inherit from RCL-CPP node. And this class will also inherit methods, that is functions and member variables from this class, and in addition to these functions and to these member variables which are inherited from node class, you will define your own functions and your own member variables. Okay, here comes the main part. Over here we are defining the constructor. So what do we do over here? The constructor name is precisely the name of the class. And what does this thing mean over here? This means that we are now explicitly calling the constructor also of the node class. This constructor will actually first create the node class, that is the parent class, and then it will start creating the part of our controller node. And what do we specify here? We are specifying the name of the node that we want to create. It is simply controller underscore node. However, you can also use any other name. Okay, so this is the constructor class. Okay, so let's explain what is inside of the constructor. This is a very important line, line 92. So let's remember that we are currently at the line 92. And in order to explain this, I need to go a little bit down. Don't worry, I'm going to show everything in this video tutorial. However, I need to scroll down and I need to go to definition of private member variables. So where they are here. Okay, so let's see what we are looking at. Over here, you have two things. You have control publisher and you have the post subscriber. This control publisher is related to the line, let's see, 92. Let me just remember the line. It's 218 and it's 92. Okay, so let's analyze and see what's written. Post subscriber is instantiated like this. Now, what do we do over here? We are actually creating an object. And you can see over here what is the data type of this object. You can see the precise definition. This means that we want to create a publisher that will publish the messages of the type twist. Remember, these are the messages for controlling our simulation, and we actually use this shared pointer, and the name is control publisher. And let's see how we instantiate or create an object of this class. We simply call this, then we call this function create underscore publisher, and note that this is actually the function from the parent node class. Then we specify the type of the messages that we want to publish. We want to publish twist messages, and we need to specify over here the topic name. We want to publish through turtle1 command velocity, and over here we specify the buffer size, and that's it. You can select the buffer size, for example, 10, 15, 20, or something similar. Okay, in this way we have created our control publisher object, and this control publisher object will be used actually to publish control messages to our turtle sim simulation. Next, we are at the line 107. So let's see what's happening over here. Now, to explain this line 107, let's go down and let's look at the private member variables over here. And let's look at this post subscriber. This is actually an object for subscribing to a certain topic and for receiving the information from that topic. In our case, the topic is actually the topic used to communicate the pose information from our virtual sensor attached to our robot. And let's see over here the type. Here you need to call RCLP CPP subscription. Then you need to specify the type of the message that you want to receive. You want to receive this type of a message. Then you need to use this share pointer, and here's the name, post subscriber. Okay, so let's go back now that we understand this part, and let's see how do we instantiate or create an object of a class. We call this, then we call the function create subscription, and again this function is actually a member function of the node class. Then we need to specify the type of the message that we expect to receive. It is the pose message. Then over here we need to specify the name of the topic. This is the topic that we figured out recently. Then we need to call this function sensor data QoS. You don't need to know too many details about this function. It's basically a predefined quality of service profile in ROS2 designed for handling sensor data systems. It prioritizes receiving the most recent data and is configured for scenarios where losing some data is acceptable in favor of low latency and high throughput. And you can change this, and you can actually specify some other parameters. However, I'm not going to discuss this in this tutorial. And then here comes a very important part. Now, when creating a subscriber, you also need to connect this subscriber with a certain callback function. Namely, every time a message comes through this topic, you need to call another function that will handle this message. And over here we are binding, and we are saying that we want to call sensor callback function. And again, this sensor callback function is actually a function of our controller node class, and we will define it later on. For the time being, we're just specifying the name of the function. Note here that we are passing as a reference. Then we need to specify the second input parameter, this, and over here we have this placeholder, and note that we use this placeholder over here. That is, we are saying that we want to use this placeholder from the STD. Currently, we will not find any role of this placeholder. That is, we will not use it in this video tutorial. However, you still have to specify it. And that's it. We created a pose subscriber. Okay, let's continue. The third step is to instantiate a timer object, and this is very, very important. So we are currently at the line 123, and then let's go back to the private member variables, and let's see where is our time object or the timer object. Here it is. Here is the data type, and here is timer object. And let's explain what is the purpose of our timer object. So let's go back here, line 123, and explain. We are calling the function createVol timer from the parent class. Then over here we need to specify the period of communication, or better to say the period of our control function. So what will happen now? Now, we are going to send or publish control informations over here every 2000 milliseconds or 2 seconds, and this will be done periodically. So by creating vol timer, we are just saying the following. We want to call a certain function with a certain period, and here we are specifying the period of 2 seconds, and over here we need to specify what we want to call. We want to call the control function, which will be defined in the SQL. And again, this control function will be the member function of our class. And as the final argument, we need to specify this. Okay, so we are still inside of our constructor. Next, let's go back. First of all, let's remember where we are. We are at the line 134, and let's look at the private member variables over here, and let's see what's happening. Okay, in the private member variables, we have this twist data structure, and I call it control velocity. This is actually the control action that's being sent to our simulation. However, since in the constructor we need to initialize all the member variables. Here I'm initializing everything with 0. Namely, this twist data structure contains x, y, and z components of the linear velocity, and it contains x, y, and z components of the angular velocity. And I'm simply initializing everything with 0, such that initially our turtle doesn't move. Next, we are at the line 146, and let's see what's happening over here. To understand this line, we have again to go back to the private member variables, and over here you will see the initial time. Okay, it is of the type RCL CPP time. So what's happening over here? I'm actually measuring the absolute time. That is, I'm just measuring the time, a moment, when actually the object of the controller node class is created or instantiated. This is very, very important. And I will keep this time, and I'm going to measure everything from this time. Note over here that this is the absolute time. And this is it. This is the end of the default constructor. Let's again go over the constructors such that you can see what's happening. This is the first part. This is the second part. And this is the third part. Okay. Next, let's see what we need to define. Let's see what is this sensor callback. Okay, so what is sensor callback? Well, if you go back over here again, you can see that when we created a subscriber, we had to specify a callback function that will be called every time a new message appears through this topic. And let's see what this subscriber is actually, or this callback function is doing. Note that this sensor callback function is a member of our controller node. That is, we are still inside of the class. So what do we receive over here? We are receiving turtle sim message pose, and I'm calling it here as received message. So what do I do here? I'm simply storing the received message inside of this private member variable last received message. Let's see, where is the last received message? Here it is. Now it's not here. Let me see. Here it is. Here is the data type and the name. So it's being stored as a private data variable. Okay, I'm simply storing it, and then what else I'm doing? I'm actually recording time of the received message. Unfortunately, pose sent by the turtle sim simulation doesn't have a timestamp, so I need to create a timestamp, and over here I'm simply creating a timestamp by recording the time the message is being received. This is actually not the time the message is being sent, this is only the time the message is being received. Now let's see again what is last received message time. It's actually a private member variable. Here it is. Perfect. Okay. So we are storing two things. We are storing the received message, and we are storing the timestamp. Now, here's one very important note. For speed, this function can be modified to use references or pointers. Since passing here by value is not the fastest option, you can either use a pointer or you can use a reference. However, then you need to use the move semantics. You will probably have to write something like this if this is a pointer. However, I didn't want to do that since I didn't want to complicate this code. So let's continue. Okay, now we implemented the sensor callback, and let's see what else we need to implement. We need to implement control function. Okay, so let's go back inside of our constructor, and let's see what is the control function. So where it is. Okay, let's go here and see. When creating a timer object, we call create vol timer, and here we bind this timer object which controls the time. It actually is ticking taka 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 every 2 seconds, and we bind this to the control function. That is, this control function is going to be called every 2 seconds, and this is our main function for controlling. That is, you can think of this function as a void control loop in Arduino or in some other microcontroller control language. So this will be your void loop that will constantly loop once you spin or start your node. So let's see what we are doing over here. we are doing several things. First of all, here we need to send the control actions. Well, here for simplicity, I'm sending constant control action. Since I didn't want to implement a complex control algorithm that will actually take into account sensor information, I'm simply sending constant since I don't want to make this video to last for 3 hours. In the next video tutorial, I'm going to explain how to implement a control algorithm. Okay, so what do we do over here? Remember that control velocity is actually the private member variable, and it is of the type twist, and we need to specify linear components and angular components of the velocities. Here I'm just saying that the linear x component will be equal to 2. That is, the robot will always locally move in the direction of the x-axis, its own local x-axis, keep in mind. And over here I'm specifying the local angular velocity, z, to be equal to 0.8, and everything else is 0. By doing that, the robot will describe a circular trajectory, and that's it. And over here I'm printing in the terminal that I'm sending the control command, and over here to send, I'm simply calling the object control publisher, its publish function, and I'm specifying the message I'm sending, control velocity. Again, control publisher is actually the object that we created or instantiated inside of our constructor, and that's it. Simple as that. Okay, let's continue. So the next thing to do is to receive the message, or basically we already received the message, however we need to print the message. So why did we receive the message? Namely, what's happening over here? If we go back to the constructor, and if you see here create subscription, this post subscriber object will always work in the background independently from the main function of our code. That is, whenever there is something or a message on this sensor topic, it's going to store this information by calling sensor callback function, and the sensor callback function, as you can see over here, is going to save everything received in this object, and it's going to save time, and this is running independently from us. That is, it's always being updated. And to print the data, we are simply going to print receive pose, and then we are going to do this. We are going to get the timestamp. We are going to type last received message time dot seconds minus initial time dot seconds. This will print the time. Then we will print the x component of the received message, that is of the received pose. You can see it over here. How I do it, I'm simply calling last received message dot x, then last received message dot y, and last received message dot theta or theta. This will print the position and orientation, and then finally I'm printing the linear velocity, and finally I'm printing the angular velocity, and simple as that. And to repeat, here you can easily implement PID controller. You will take the received pose information. Let me just close this. You will take the received pose information, and this is your feedback loop. And then over here, instead of constant control velocity, you're going to implement a function that will implement control signals. Simple as that. Okay, so this was our control function. And over here we have the private member variables, which we actually explained by explaining the corresponding functions and constructor, and that's it. Note where the class starts. So the class starts somewhere over here, line 82, and ends at, let me see, at a line 222. Now erase maybe 100 lines of comments, and you will end up with maybe 100 lines of code for this class or something similar. And here's our main function. It's very similar. This part is standard. Then over here we need to initialize RCLCPP, and you always need to do this. That is, you just call this function and everything is set, and you can continue further. Then you need to create a node. You do it like this. You called std make shared, and over here you specify the type of the node, since this is a template pointer, controller node. and that's it. Here you instantiate the test node. This is your node. Then what you need to do, you need to spin that node. This will start the node. So let's see what will happen. Once you start the node, the first part that will be executed is actually this constructor over here. First of all, the constructor of the parent class will be called, then this constructor will be executed, then you will do this, create subscriber, publisher, timer object, then already over here, the subscriber will start ticking in the background and you will start updating corresponding member variables. You create a vol timer, then you set and initialize everything, you measure time, and then sensor callback will be automatically called every 2 seconds. That is the vol timer function will call the not the sensor. I have to be careful. The sensor callback. So here's the correction. The sensor callback will actually be called by this part over here, the post subscriber. However, the control function will be actually called by the timer, the vol timer, and that's it. And let's go back here. Once we spin the node and the node is running, and it will run for infinite amount of time until something happened, until your computer restarts or a person press Ctrl C. When the person press Ctrl C, what will happen? Now, the code will not immediately exit. First of all, this part over here will make sure that everything is removed from memory. That is, that everything is clean, that all the nodes destroyed, all the reserved memory is destroyed, and then you will gradually, in a nicely, in elegant manner, exit your code. And that's it. Simple as that. Might look complex, right? But it's actually very simple because this is basically a template C++ class I wrote. And again, you can start modifying this part over here and implement your controller. Next, make sure that you save this file and we need to proceed with the next step. In the next step, we need to modify cmakelist.txt and package.xml files. So let's learn how to do that and let's explain why we are doing that. First, let's open cmake file. So click on File and let's open File. Then over here, the cmake file is located in the base folder of the test_node package. And here it is. To show you in the terminal where it is, you need to go one step back over here and then you need to type this. And here it is. Okay, so let's open the file by clicking on the file and let's see what needs to be done. First of all, over here we need to tell to cmake build system that we need to add the dependencies. That is, our new node or our new package will depend on several standard ROS2 packages, and these packages are RCL CPP, turtle sim, and geometry message. Namely, if you click over here and if you go all the way up to the header files, you will see that we are including RCL CPP, geometry messages, and turtle sim. All these header files are actually header files from other packages. These packages are installed on your system, they exist. However, you need to explicitly tell to the cmake system or the build C++ system to include these dependencies. So let's start and let's do that. Okay, so here you need to find package m and cmake required, and you need to add these 3 lines. So let's add these lines like this. Okay, and now these packages are being added as dependencies. However, the story doesn't end here. You need to define an executable for your program. To do that, you need to add this line, and I'm going to add it over here and explain what's happening. Namely, what are you saying over here? You want the executable to be called test_program. And this is exactly the executable that's being set or defined or written when you called ROS2 run, the name of the package and the name of the executable. And you need to link this executable to the test.cpp, that is to the source file. This source file, test.cpp, is in the source folder. That is over here. You need to specify the relative path, and again the relative path is with respect to the cmake lists file. Okay, However, the story doesn't end there. We still need to do several modifications. Now, here we need to add this line. Let me now go here, right? And I need to add this line. What will happen over here? Here again, you have to say that your test program, that is this executable, depends on the standard packages RCL CPP, geometry message, and turtle sim. And that's it. Make sure that you save this file and let's continue further. Okay, we still need to make one final modification, and sometimes I forget this, but it's luckily I have this manual and I will not forget it. Now, what is also very, very, very important? It's very important to tell to CMake system where to place the executable files. And usually the standard destination is defined like this. That is, I added this line, you specify install targets, then you specify the name of the executable, and over here you specify destination. It's going to be in the library folder, and the name will be project_name. Later on, the executable will be placed there and you will be able to execute it. Next, make sure that you save this file and let's continue further. Okay, the next step is to modify package.xml. Okay, so where is this file? Well, this file is located over here. You can see the path. However, let's open it from Visual Studio Code. Click on File, Open File, and let's open it. And here we have to do several modifications. We need to add actually 3 lines, and here are the lines we need to add. We need to specify here again the dependencies, and over here let's add them after line 13, and let's put them over here and let's save. Here optionally you can also change version number, you can add description, you can set your email over here, and you can add the license. I will not do that in the interest of brevity. Save this file and we can continue. And finally, we have reached the final step, right? Hopefully you're not tired by now. So make sure that you're in the base workspace folder. You can either do it like this by 2 times pressing CD, and then you will be in the workspace folder, or you can simply type this and this will lead you to the workspace folder. Again, this is the terminal where you source the environment so you can run everything. That is, this is the terminal where you created an underlay, so keep in mind that. Okay, but before we build everything, let's make sure that everything is okay. Luckily, we have a very nice tool called ROS2, and you can install this ROS2 tool by typing this, enter your password. Then to initialize ROS2, you simply need to type this, ignore this error, and update the ROS2 just in case that ROS2 is obsolete, which shouldn't be. However, let's update for a second. ROS2 is a very important command, since ROS2 will verify that you have properly set all the dependencies in CMake and in the other file package.xml. And to do that, you simply need to execute this command, and let's see what will happen. You will see all required ROS2 installed successfully. That is, all the dependencies are installed on your system and we can proceed. Okay. Let's now build everything. Again, make sure that you are in the base workspace folder by typing this. And then over here to build everything, we simply need to type this. build --packages, select. Here we are going to build only single package, and that's the package we created. And press enter, and let's hope there will be no errors. Let's see. 5-6 seconds, everything so far so good, finished, no errors, no warnings, and we are good to go. If you have the errors, most likely the errors come from the implementation file over here. Spend some time studying this implementation file. I actually explained completely this file, and type it by yourself, or you can use the codes I posted in the description below. Okay, the next step is actually to run this node and to run the program. So let's learn how to do that. Well, To do that, open a new terminal. Let me now resize this over here. So open a new terminal window, and inside of this terminal window, you first need to source the environment. To source the environment, you need to type this. However, let's just go back to the home folder and be careful over here, and let's explain what you're sourcing. Let's look at the command. Here, you're not creating an underlay. That is, you're not sourcing the setup.bash file from the classical ROS2 installation. You're actually sourcing setup.bash file from your newly created package and from your newly created node. So keep in mind that thing. Here you're creating an overlay, and that's the only thing you need to do. And then let's run our node. To run the node, you simply need to type this command. ROS2 run, then you need to specify the name of the package and the name of the executable, and bang. Let's see what will happen. Aha, beautiful. But where is our simulation? Well, if you click here, you will see that everything moves nicely. It's so beautiful. You can see how it moves. It's amazing. Okay, while this thing is running, let's learn how to obtain more information about this simulation and to verify that everything works as it should work. So open a new terminal, and in this new terminal, create an underlay by sourcing this file. Here you're sourcing the basic ROS2 installation setup.bash file. You're not sourcing your newly created package. Let's list the topics to make sure that everything is as it should. So we see the topics, command velocity and pose, perfect. Let's see the nodes. This is also very important. We can see controller node. This is the implementation we just created, and we can see turtle sim. Good. Let's see what's being sent through the ROS2 topic echo, or better to say what's being sent through turtle1 command velocity. If you press this, you'll see in real time what's being sent. You can see that every 2 seconds we are sending this twist message, and that's precisely what our code is generating. Namely, if you go over here and if you scroll down over here in the control function, we are actually sending precisely that, and that's precisely what you're seeing over here. Good. You can press Ctrl C to stop the echo command, and let's continue. And finally, let's visualize the structure of our graph. First of all, let's update everything. Let's type this. Oops, I need to make my password. Oops. Okay, so let me see now. Okay, anyway, this is not necessary to update. I just need to install this. And let me enter the password. Okay, that's it. And let's see the RQT graph. Here it is. And here's the graph. You can see the graph over here works perfectly. Note over here that this password that you saw for a moment is actually not my password. Okay, just keep in mind that thing. So what you can see over here is the RQT graph, and this is very important since you can see our controller node, you can see the turtle sim, and you can see the communication between these two nodes. You can see the control topic and you can see the sensor topic, and that's it. Okay, that's all for today, and I hope that you liked this video. This was an amazing tutorial. It took me a significant amount of time to create this tutorial. I hope that you enjoy it and that you find it useful.